Dusty record button, and look at that, we are recording. Yes, it works.
Cool. Yay!
They have really good IT help at OTC, I will say that. They're pretty good.
Oh, that's good.
Always tell students too, if they're having any problems, you know, working Zoom or working any of this stuff, just give those guys a call. They lead you right through it step by step. Of course, it didn't help last week. It was all too late. So I made sure yesterday I got all set up, and they told me the problem that I was doing was I was trying to always access Zoom the same way you are. When I send you the link and you guys get it in your email or whatever in the announcements, I can't use that.
Right.
That opens up the students.
You have to go.
I have to go through a different doorway. So I have to go in through
You have to be the administrator.
Yeah. So anyway, that's what screwed that up. But here we are. So it works. So we'll cover some acoustics today. We'll delve right into this whole frequency business, and we'll get right into it. I'm going to share screen here and show you a PowerPoint slide. Share the screen, and let's see if I can't pull up a PowerPoint here. And you may be able to see this, right? You see all these weird little slides here? Okay.
Yep.
When we talk about frequency, and I hope people have printed up their trusty dusty little papers here, because that's what I'm going to be talking to you all from. And in the whole course, what we're going to be covering for the first half of the course is physics or physical acoustics, like sound waves, the decibel, frequency, the speed of sound, all of that stuff, the actual physics of sound. Then we have our midterm, and then after the midterm, we really focus on the psychoacoustics, or the perception of sound. But first and foremost, why don't we just home in on this puppy right here, and we'll look right at that slide. And what you're seeing there is a good old tuning fork. That's just like I'm holding in my hand. And when you ding a tuning fork, don't know if you can hear that, but at any rate, when you ding a tuning fork, the tines, or the forks, are wiggling back and forth really quickly. And when they're wiggling back really quickly, what you're seeing here, can you see my little cursor when I move it across here? Are you guys able? Okay.
Yeah.
You'll see this squeezing and separating of molecules. Those are sound waves. So sound waves don't really go up and down like this, because if they did, we'd all be doing this stuff while we hear each other. I mean, what sound waves are squeezing and separating of molecules. And the squeezing together is, they sometimes call it compression. Sometimes they call it condensation. Same thing, condensation, compression, and the separation is the rarefaction. So one compression or one condensation and one separation make one wavelength. And I'll show you what a wavelength can look like. A wavelength, have a look at this picture here. This is just a few slides into your PowerPoint. And here you, once again, you can see the squeezing, separating, and we draw them as if the sound goes up and down, up and down. Always on a sound wave, the up portion represents the condensation, or the squeezing of molecules, always. The down portion represents the separation, or the rarefaction. Okay, so basically that's the nuts and bolts of what sound waves are. So if we look at our notes here, and I'll just escape here and go right to my notes here and just see what we've got. And when you're looking at the page here, and I'm looking at the same notes you are, the share screen stuff works pretty good. I gotta say, this is you can see this here? You all able to see that?
Yeah, yeah.
You know, and you see this word sinusoids at the top. Never freak. It just means sound waves. It comes from the word sinus. Your sinuses behind your nose bend. They're all they're bending little tunnels. And in Latin, sinus means bends. Okay? Like a snake in the grass. It's got bends. Now, frequency / period. We'll talk about that later just before we get out of here today. Wavelength, speed of sound, sound fields, resonance, and impedance. I think today we'll probably get through about half of those. And then next week we'll finish this section. But here we go. In this course, we will cover the physical properties of sound, acoustics. Physically, oh gosh, you gotta like this sound. Physically, sound is a propagated change in the density of an elastic medium. There you go. How do you like that? Good.
Sounds pretty good.
Propagated change just means this. I did it. Something made it happen. If a tree falls in the woods and nobody's there, is there a sound? Yes, there is, because what is physics? What is sound? It's a propagated change in the density of an elastic medium. Well, here's the elastic medium. It's this here. It's this guy, the air. The air is your elastic medium. And elastic doesn't really mean elastic bands or rubber bands. Elasticity just means that the air can be moved. It can be squeezed and separated. Propagated just means it was forced. The tree fell down. Bam! And what did the tree...
Would you say...
Go ahead.
Would you say that elastic, you could use flexible as a synonym maybe?
Well, you're going to get more definition about it in just a second, but I'll say this. Elasticity is the ability to resist being deformed. The ability to resist the fact that the air doesn't want to move back and forth, but you made it move back and forth. Okay? So it's the forced or propagated change in the density, and if you look at my fingers, they're all molecules, and all the molecules in air are equally separated apart. Hi there, Lizzie, just a new joiner. Here we go, good stuff. And so all the molecules moving around in air are evenly spread apart. And then suddenly something went dong and made a change. And now all of a sudden, what do you have on your screen? You have a pattern. And that pattern is sound waves. Okay? So sound doesn't happen by itself. Something made it happen. The tree fell in the woods, or I dinged a tuning fork on my head. Whatever the heck it is, doesn't matter. Sound is a propagated change in the density of the molecules, how close they are together. It's a change in that density of an elastic medium, of a medium like air that can be changed. It doesn't want to change, but you forced it to change. Enough on that. Second paragraph on your page. Well, you beat to death a dead horse here. Simple wave motion in air. Brownian motion, that's just the random movement of molecules in air, the way they are with no sound going through them. As heat is increased, molecules move faster, blah, blah, blah. Who cares? Don't worry about that. Propagation. Strike a tuning fork. Something has to cause or propagate an abrupt change. The movement of the fork tines, the movement of these guys that I'm looking at right here, this tuning fork, the movement of these tines back and forth, it continues past the center. It continues past the center. You can just see that here. It goes past the center. And it goes back over here, back over here, back over here, until it stops moving. Okay, that's it, just basically it. Escape, back to your notes. Inertia, blah, 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 blah. Ability to recover from being distorted. Who cares? Don't worry about that. In the air or in any elastic medium, in any medium that would resist being changed, the first molecules to be disturbed hit the other ones next to them, and these hit other ones, and so on. After disturbing their neighbors, the molecules bounce back, blah, 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 blah. Okay, sound waves, a series of squeezed, see that? Condensed, and then spread out, rarefacted molecules. And that's where this is, condensation, rarefaction. Okay? Next slide. Here's another picture of the same thing. showing you the very same thing, just a different kind of a picture. You can see the condensation is where the molecules are tighter. The rarefaction is where the molecules are looser. That's it. Waves. How do waves of sound differ from light waves? Now get this. I mean, here's a wave, a long wave, and it gets shorter and shorter and shorter and shorter. Light is really weird. Light is, you know, when you know who you're not, you get a better idea of who we are. Okay? Look on the left, you've got radio waves, short waves, television radio waves, microwaves in your kitchen. Okay? And then telemetry waves, infrared waves, and all of a sudden now you're in the rainbow. Now you're in the light that we can see. And we only see a narrow band of light with our eyeballs, okay? Then once we get out of our wavelength, the waves get shorter. They keep getting shorter. See, the waves are long on the left, and they get shorter, shorter, shorter. Then you get into ultraviolet. We can't see it anymore. And then you get into X-rays, gamma rays. Well, sound ain't light. Light can travel through outer space. That's why you can see stars. That's why you see the moon, because light can travel through a vacuum. Light doesn't need a medium to travel through. Light can travel through anything, and it just goes through space. Otherwise, we would look up at the sky at night and it'd be totally black, okay? So, but sound waves are different. See, this is another picture showing you visible light. On the left, you've got red, and on the right, you've got purple or ultraviolet. And that's only a slim band of light. Light has lots of waves, okay? Do I hear, or I thought I heard somebody talk? Oh, no worries, okay. So, but sound waves are different. Sound requires a medium to travel through. It's got to travel through air, or it's got to travel through water. That's how dolphins and whales talk to each other, through the water. Or sound can travel through steel. You know the old saying, someone says, oh, I'm looking for work. And your friend says, oh, I'll put my ear to the ground for you. You know, I'll listen to the ground, okay? That's what the First Nations Indians did when they were listening for the buffalo. They'd put their ear to the ground because sound would travel through the ground, and they'd listen for the hoofbeats. When you put your ear on a railroad track, you can hear the train quicker through the railroad track. Sound can travel through steel. So, but sound needs a medium to travel through. Sound can't travel through outer space. So if you and I were out in outer space or standing on the moon, we would not be able to talk to each other because sound requires air or something to make waves in. You see? That's the difference. Now that we've covered that, just keep it basic, okay? Because that's how I think too. Middle of page 1, and I'm going to go back to middle of page 1 here. I'll move my cursor down here. Sound waves, longitudinal and transverse. Put a circle around that one, okay? Sound waves aren't like water waves. Water waves are transverse. Water waves go up and down like this, right? And the up and down movement of water waves like this is perpendicular to the direction the wave is traveling. So when you're standing on a beach and the wave is, it's coming at you, okay? The wave goes up and down, but it's perpendicular to the direction of the wave. And so waves like this, waves like these here, like on the bottom, you'll see the picture here on the bottom, that's a transverse wave. It's going up and down, up and down, and the direction of the wave is going this way, okay? Water waves. We draw sound as if it's like water waves, but we know in our heads, really, sound isn't that. It's longitudinal waves, like the top. The squeezing and separating are parallel to the direction you're moving. I mean, what are you saying? It's not going up and down, Okay, the wave is rather like an accordion. That's what longitudinal waves are. We draw sound waves up and down because it's easier. I don't want to sit there going with a pencil and because it's a pain in the ass. Okay, it's way easier to draw it. But just always remember, the up of a sound wave is the squeezing of the molecules. The down of the sound waves is the rarefaction or separation of the molecules. That's the difference, okay? Next section on our typed writing notes. Bottom of the page. I'm going to just ask you to think of sound waves as like, this gets kind of weird and complicated, but don't freak. Sound waves are sort of like a circle. Let's see if before I go to that, I'm just showing you a speaker here. This is just another picture. We'll get to that in just a sec. So here's a speaker, and the bottom one's a speaker. And you see how the top speaker, it's making a squeezing of molecules, a separating of molecules, a squeezing of molecules. And look at the sound wave that we draw. Up and down, up and down. This is a long sound wave. And this would be what's called a low frequency. Low, as in bass. Low frequencies have long sound waves, low pitches. Low frequencies have long condensations and long rarefactions, okay? Look at the bottom one here. This speaker is making a high-pitched sound, and its condensation and its rarefaction are skinnier. So its wave, the way we draw it on the right, goes up and down more often. Okay, so when you think of a sound wave, the vertical represents its amplitude, how tightly the waves were squeezed together, how separated. Okay, time is represented horizontally. Time is always on the horizontal. Amplitude is always on the vertical. So the speaker making a low-pitched sound, we call that a long sound wave, a big condensation, big wide rarefaction, a big black area, a big white area. Whereas the high-pitched sound coming out of the bottom speaker, you have a skinny black area, skinny white area, skinny black area, skinny white area. So your wave is shorter. So low frequencies have long waves, high frequencies have short waves. Always remember that. And let's draw it to the animal kingdom. Just for fun, I'm going to stop sharing my screen for a second here and just talk to you all as a group. Bats are blind, right? Bats can't see. How do bats catch flies? How do they catch flies? They fly at night and they eat. Okay? What they're doing is they are emitting high-pitched sounds, very high-pitched sounds. And the sounds have short, little, really short waves. And short sound waves bounce off of things. Ding, 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 ding. So they use it like radar. They're spitting out high-pitched sounds that we can't even hear, and the high-pitched sounds are bouncing off of the flies or the bugs, and that's how they locate where the bugs are while they're flying. That's how they eat them. The opposite part of the animal kingdom, think of elephants. Big, long-trunked, elephants emit low frequency sounds, and the sound waves are so long, they're yards long, they're like at least as long as your room, your living room. Okay, and those long sound waves, they don't bounce, they bend around things. They bend, they go over rocks and trees down into the next valley below. And that's how trains of elephants follow each other miles apart, and they know exactly where they are. Zoologists would fly over with helicopters going, how do they do that? We now figured out how. They emit low-pitched sounds. Low pitches bend, high frequencies bounce. And you know what? This relates directly to hearing aids. Have you ever heard someone's hearing aid whistle? Someone's wearing hearing aids and they're... Well, that is high-pitched sounds with short little wavelengths are bouncing out of the hearing aid, or they're bouncing off the person's eardrum, and they're leaking between the hearing aid and his ear canal, and they're getting picked up by the mic, amplified again, bouncing off the drum, leaking out, picking up by the mic, bouncing off the drum. You get in that circle. High pitches cause in hearing aids. How come? Because they have short wavelengths. Highs bounce, lows bend. Just thought I'd tell you that. So now we get to the bottom part of our page, and you're looking at something that gets a little kind of technical here, but we won't worry about it. It's this bottom part, it's this piece here. Okay? And you're looking at this slide in your PowerPoints, and in your notes, it's the bottom third of page 1. So in your notes, we're looking right over here at the bottom part, sine waves and degrees of phase, that section, okay? And our PowerPoint, we're looking at this slide. Look at the circle on the left. See how you can start at 0 here, and you go to 90 degrees, 180 degrees, 270, and right back to 0 again. You know when people speed around in a parking lot and they do a 360? Okay, a 360 is a circle. A circle has 360 degrees. Well, if you take the top half of the circle and bend it away from the other half, guess what? You've got a wave starting at 0, going to 90, going to 180, going to 270, and back to 360 again. Get it? So just like a circle has 360 degrees, one wavelength, one condensation, one rarefaction. The condensation is the bump on top. The rarefaction is the valley that follows. And guess what? Now the wave will just repeat the same thing. It'll just do the same thing. Ad infinitum. But one condensation, one rarefaction is 360 degrees.
Can I ask a quick question?
Yes.
On the diagram with the 0 starting, okay, just the regular wave picture on the right-hand side, you've got the 0 and the 0, so you've got the 0 starting at the left, up for the condensation, down for the rarefaction, and back to 0. On the circle, we're going counterclockwise.
Yeah, I don't know why. Yeah.
Okay, I was just going to ask if that was because you moved because you're going in time, you're going forward, so you're taking that first 0 and matching it up, or is it just?
It's just the drawing.
Okay.
It's just the guy was maybe left-handed. I don't know. I'm just teasing. I don't know.
Okay.
But it's fair enough. One thing I do want to mention to you, though, we won't get bogged too much down in that, because that would take us into physics, and you know what? Okay. I won't even go there. But do notice that how this wave on the right-hand side is kind of pointed, and the bottom is kind of pointed. It's not like totally, it's not quite like these. Look at these. They're totally round. Totally round. In all actuality, sound waves, see how the black area is really tight just in the very center? Okay, and the black area really tight just in the very center. That is more accurately shown by a wave drawn like this one here on the right. Okay, but
so it actually has a peak and a valley.
It actually has peaks, instead of just a trough. But you know what? That gets into, again, out of the scope of what we care about. We're looking at getting our hearing instrument specialist designations, and we're not physicists. So that's all I'm going to say about that bottom third of the page. Next, here you go. This is a simpler picture. Back to normalcy. Again, look at one wave, one denotation of a sound wave into 360 degrees. There you go. Starting at 0, 90, 180, 270, back to 360. Okay, now you can call that 0 again. It would go up to 90, And here's another wave. It's starting in a different phase. Look at this wave compared to this one. This one here, or this one. They're both sound waves. They're both sine waves. Sine wave, sound wave, doesn't matter. Remember, sine just means bend, doesn't matter, okay? This wave just happens to be at a different phase. It's starting here, now it's going down, and then over here, and then up. Do you know what would happen if you added this wave here and this wave here together? You'd get the sound of one hand clapping. Ha ha, silence. We'll talk about that in a bit. So this sinusoid begins at 180. Well, it doesn't mean it's not a nice sound wave. It's just started at a different phase. Who cares? Here, look at this sound wave. There's a third one. It's got 360 degrees too. But look at it, started at 90 degrees. And then went over to here, and to here, and here, and here. But it's got one cycle. This wave has one cycle. This wave has one cycle. This wave has one cycle. They all have one condensation, one rarefaction. Okay, this one here is an interesting display. I mean, but it includes 360 degrees as well. So it's one cycle. One condensation, one rarefaction is known as a cycle. It's known as one wavelength. And now we're ready to talk frequency. Now we're ready to talk frequency. High frequencies have many cycles, many waves per second. Low frequencies have fewer cycles, fewer wavelengths per second. So look at this slide. This is a good one to compare the three. I'm hearing some voices, but anyway, look at these three pictures here. The top pair, the middle pair, and the bottom pair. The top pair are equal in amplitude, aren't they? They're equal in size, okay? So they're the same loudness. You'll hear them both just as loud as each other because their up and down has the same height. But one of these wavelengths is longer. You see that? This one here, the one I'm drawing my cursor on. This one has longer wavelengths, longer condensations, longer rarefactions. So it is going to be more bass. Whereas the wave behind is going to have more condensations. So let's call this 1 second. How many bumps per second? The one with more bumps per second is higher up in frequency. The one with fewer bumps per second is lower. Look at the middle pair. Are they different in height? I'll ask you.
No.
Is there a different amount of bumps per that unit of time? No. They sound the same in loudness. They're going to sound the same in frequency. They're just a little bit out of phase with each other. Little bit out of phase. You might hear kind of like, you might hear sort of a wobble sort of in there, okay? Look at the bottom pair. The bottom pair, do you see the same amount of bumps? Yeah, I do.
Yeah.
What's different about these? Are they different in phase? No, they're just different in intensity. One's softer than the other. And this highlights the 3 dimensions of sound. Sound takes place in frequency, amplitude, and time. Frequency, amplitude, and time. And all three dimensions are shown right here in this slide. Okay? They can be different in amplitude, they can be different in phase, that's time, or they can be different in frequency. Doesn't matter. Here's another slide showing you the same thing. Have a look here. The top pair, same in frequency, different in amplitude. One's going to sound louder. The middle pair, same in amplitude, different in frequency. If this is 1 second from left to right, all these are 1 second long. All wavelengths, remember, the horizontal is time, and the vertical is frequency. And you know, frequency doesn't just have to pertain to sound. Frequency, you can think of what's the frequency of your footsteps? How many footsteps are you taking per second? Are you running? Da, 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 da. Are you walking slowly? What's the frequency of your footsteps? So what's frequency? You define a time. Is it a minute? Is it a second? Is it whatever? And then how many times does something happen per that unit of time? With sound, the unit is always a second. How many bumps per second? How many wavelengths per second? And again, looking at this slide, you've got the 3 dimensions of sound shown right here. Amplitude, and the middle one is frequency, and the bottom one is phase or time. If you played these 2 tones together, they'd cancel each other out. You would have no sound whatsoever. Okay? So that's an important concept to remember. Now we get to the top of page 2 in our notes, and we could call this 2 ways of representing sound. I'm going to put on my glasses here and take a peek down the highway of page 2. So over the whole bottom third of the page, don't worry about that. I'll never be asking about anything on that bottom third of the page at all. That's just FYI, for your information. That was describing how the sound waves are actually a little more pointed at the top and bottom. That's all we care about. Enough on that. 2 ways to represent sound. Waveform, like we've been looking at, those are sound waves. And always the x-axis, x means horizontal, y means vertical, okay? We all know that from math in high school, okay? The x-axis is horizontal, vertical axis is the y-axis. So we've talked about sound waves, and we will for some time yet. Next week and going on, we will keep on talking sound waves. It's easy, read with me, it's easy to see sound as it changes over time. It's easy to see as it changes but it's hard to tell the individual frequencies very well. It's hard to see the actual frequencies. Now, well, look at this. Look at these waves here. What's the frequency of the top pair? Well, shoot, you got to say, okay, is that a second? Okay, how many bumps? 1, 2, 3, 4. So you got to sit there counting. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll call it 10. It's got 10 cycles per second. How many does the middle one have? 1, 2, 3, 4, 5. It's got 5 cycles per second. But you always have to sit there counting. You're always kind of you gotta take a peek at that always. So sound waves, you can see the frequency, but it's a little tougher sometimes to see the actual frequency. Another way to show sound is here. This is a spectrum. This is another way to show sound. And you're going to see this all the way through your HIS course. Okay? When you're looking at this, horizontal frequency. And look at over here. You can see the horizontal axis.
Ted,
we're getting a lot of sound.
You might want to ask Nisha to.
Yeah, Nisha, can you hear me? Nisha, can you hear me? Hello, Tata Nisha Spears, can you hear me? Hello, can you hear me? I don't think they can. Good question, Kelly. I don't know. I'm not sure. At any rate, we'll keep on working at that. I'll send her an email later. Okay, the other way to look at sound, okay, the other way to think about sound is on a spectrum. This is called a spectrum. It's not a sound wave. Here you're showing individual sounds, and this one might have 100 cycles per second, and 200 cycles per second, and 300 wavelengths per second, and so on. 400 cycles, 400 condensation rarefaction, and 500, and so on. And you can see that here, then they're calling that the frequency. And notice frequency always is abbreviated HZ. HZ stands for Hertz. H-E-R-T-Z. Okay, Hertz. capital H, small z. This means cycles per second. That's what hertz is, okay? And look at the vertical axis. It's called decibels, amplitude. And amplitude of sound is always called decibels, little d, big B. So hertz, big H, small z, decibel, small d, big B. And we're going to be covering the decibel in 2 weeks from now. Not next week, but 2 weeks from now, we will descend into the decibel from hell. Okay, but right now, focus on the fact that there's 2 ways to represent sound. Sound waves and sound spectrums. Now, sound waves, it's hard, we said, to see frequency. You have to kind of look at the wave and count and wave and how many bumps did you see. Look at this. Do you see all time represented on here? I don't. Where's time? I see 2 dimensions of sound, but I don't see time. I see amplitude and I see frequency. That's because a spectrum is like a slice. I'm going to stop sharing screen here and talk to your faces again. A spectrum is like a slice of bread. If you think of a loaf of bread as the sound wave, that's the loaf of bread. A spectrum is like taking a slice of bread out and turning it sideways so you can see the raisins. Okay? So a spectrum is like, doesn't include time. It's just a slice of time of that sound wave. You're going, and you're going, turning it sideways. So you can see that you need 2 different drawings to show all 3 dimensions, because a wavelength just shows 2. Nisha, can you hear me, Nisha?
Oh, hi.
Hi.
Yes, I can. Can you hear me?
Yes, I can. I was wondering, because we had a lot of noise from your end for a while. I was trying to ask you to see, but that's all. Just now we know. Okay, great to meet you. Good to see you. Glad you can hear me okay.
Well.
Okay, cheers.
Yeah. You want me to put it on mute?
Yeah, you could if there's a lot of noise, and that would be great. Thank you so much.
I will. Thank
Excellent. But if you have a question, don't hesitate to ask. Okay. Now, so a sound wave you can think of as the loaf of bread, and a slice of that bread turned sideways so you can see the raisins in it. That would show the spectrum. So a spectrum is a wonderful way of showing exactly what sounds are in a sound, what frequencies are in it. It just, there it is. Okay, we will return to this topic in a few weeks, but you heard it first here. Okay, now we've got to, now when we look at the second paragraph of page, here, I'll stop sharing here for a second. Oh yeah, hang on, let me share again, but I wanted to get to a different, I want to show you something different. Okay, let's see. There, finally got out of that. It wouldn't let me at first. Okay, look at this next paragraph here. Amplitude, frequency, and phase. Again, note the 3 different things. We showed you the picture with those, I'll go back here. We showed you this picture right here, where you saw amplitude, frequency, and phase. That's what that second paragraph is talking about here. Sound takes place over 3 dimensions. Time, amplitude, frequency. Now we've got to get to the meat of today. Frequency and period. Frequency, we'll read this first, then I'll show you the PowerPoint slides and we'll read it again, okay? Frequency, the number of times something happens per some unit of time. It could be your footsteps, doesn't matter. But for sound, frequency refers to the number of cycles per second. Good. Hertz, capital H, small z. 1 hertz is 1 cycle per second. For example, with a sound with a frequency of 100 cycles per second, that's 100 hertz. You see that? 100 hertz. Period. That's the flip side. Period is the time on your watch. How many seconds? The time it took to complete 1 cycle. Hertz is the number of cycles per second. Period is the time it took to complete one cycle. So for example, if a sound is 1 hertz, its period is 1 second. It took 1 second to make one cycle. If a sound is 100 hertz, then its period is 1/100th of a second, because you had 100 bumps in 1 second. So the time it took to complete one bump in one valley is 1/100th of a second. So period and frequency are inversely related. The longer the wavelength, the lower the frequency, the fewer the hertz, the longer the time it took to complete one cycle. The higher the frequency, the shorter the time it took to complete one cycle. The lower the frequency, the longer the period. Higher the frequency, the shorter the period. So what it says right in the middle, frequency and period are inversely related. As frequency is increased, period is decreased, and vice versa. Mathematically, frequency is 1 over the period. Period is 1 over the frequency. It's just quite simple. Frequency, 10 hertz. Let's pretend it's 10 hertz. What's the period of a 10 hertz sound? 10 is equal to 1, okay, over the period. So 10, it would be like 1/10 of a second. 1 over 10. So frequency is, so humans here, and we're going to work this out, we'll try a few of these, but as frequency is increased, the period is decreased, and vice versa. Frequency is 1 over the period, period is 1 over the frequency. So if the frequency is 10 hertz, its period is going to be 1/10 of a second. What's a 1/10? 1 over, and look at the right-hand side, the period. If it's 1/10 of a second, that's going to equal to 10 hertz. So basically, when you're looking at humans, what do humans hear? Humans hear from as low as 20 cycles per second to 20,000 cycles per second. 20 cycles per second to 20,000 cycles per second. So we don't hear down to 1 hertz. We can't do that. It's too low. Elephants can hear that. 2 hertz, 3 hertz, elephants can hear that. We can't. But as soon as it gets to 20 cycles per second, we begin to almost feel it. We can kind of feel it, like a foghorn blowing or something. It's just, you just about feel that. And then we hear way up into the treble, high pitches of 20,000 cycles per second. That's getting into the range where dogs and cats can hear, but they can hear higher up than we can. We can't hear beyond 20,000 hertz. And guess what? As we get older by the decade, as we get older, from 10 years to 20 years, to 30 years, we lose our ability to hear treble. We can't hear 20,000 anymore. And by the time you're 10, yeah, you can't hear 20,000 anymore. By the time you're 20, you can't really hear 15,000 very well anymore. By the time you're 30, 15,000 is kind of getting hard to hear. By the time you're 40, by the time you're 50, and once you get to be about 60, about my age, then all of a sudden, you begin to have trouble hearing up to 8,000 hertz. Look what it says in italics here. Hearing tests, the ones you're going to learn how to do on people, okay? Hearing tests only look at from about 125 hertz. We don't bother with 20 hertz, it's too low. Speech isn't even in there. What do hard of hearing people have trouble hearing? They have trouble hearing speech, okay? So what we care about is testing from 125. And if anyone is musically inclined, 125 is low C on a piano. 250 is middle C on a piano. 500 hertz is high C on a piano. You can tell it when I'm doubling the numbers each time. And that's what we do in hearing tests. We test at 125, we test at 250, we test at 500, we test at 1,000. Now you double 1,000, what do you got? 2,000? Double that, what do you have? 4,000? And lastly, 8,000. And when you hit 60, your high pitches have lost. Now you're losing the ability to hear 8,000 and 4,000. And guess what you're having trouble hearing then? The letter S. S. The letters SH. Sh. I'm going to stop sharing screen and get personal here. You're going to have trouble hearing TH, K, CH. So all the high-pitched sounds. Okay, think of these words: hat, sat, bat, cat. They all have ah, but what makes them different? High-pitched consonants. The letters that form around the vowels. See, vowels are cheap. Vowels are loud from your throat, and vowels, I-ya-o, A-E-I-O-U, and sometimes Y. Vowels are loud and low. So elderly people have no problem hearing vowels. They have problems hearing treble. They have trouble with treble. So they think, oh, you young kids are mumbling. Kids mumble today. Yeah, they can't. They don't speak clearly. Well, it's true. A lot of kids do mumble, but the coin has two sides. On the other side of the coin is the elderly person can't hear. So all the sounds of speech, all the how to me, they kind of sound like this. They hear all the vowels, but they're saying, I just can't hear what you said. Did you say dishes or fishes? Did you say kittens or mittens? So when a hard of hearing person is always catching up to what must have been heard, that person gets tired. And that person feels alone. And that person says, you guys go on out and have a good time. I'm going to stay back and read a book.
I have a
That's
question.
the sad part of hearing loss, especially for the elderly. Helen Keller said, blindness cuts people off from things. Hearing loss cuts people off from other people. Hearing loss is the one sense that not only affects the person who's got it, it affects others around him or her. It affects human relationships. It affects husband and wife relationships, spouse and caregiver relationships. You're in a really cool field. This is a touching and a very scientific field, and also a very heartfelt field. It's got a bit of both to it. It's really kind of cool, I think. But back to frequency and back to period. We should look at these, okay? So let's say you have a sound, and it is 100 hertz. You want to figure out the period. Period equals 1 divided by 100 hertz. And get your calculator out. 1 divided by 100 is going to give you 0.01. Okay? So 1/100th of a second. Okay? Take a 500 hertz sound. What's its period? What's the length of time required to complete one cycle of a 500 hertz sound? Well, period is equal to 1/f. Period is equal to 1 divided by 500. Well, get my calculator out here. 1 divided by 500 equals 0.002. 0.002. That's 2 1,000ths of a second. 0.002 is 2 1,000ths of a second. Okay? Take a 50 hertz tone. Go 50. What's the period of a 50 hertz tone? 1 divided by 50 equals 0.02 seconds. That's 2 100ths of a second. Every time you put another decimal in front, you've gone now to thousandths. So back to 500. What's the period of a 500 hertz tone? 1 divided by 500 equals 0.002. That's 2 milliseconds. Now come north of the border to Canada, where I'm from, where we don't say the last letter Z, we call it Z. Okay, that's what Canadians do. I'll stop sharing and I'll start talking to you. Okay, so we talk in metric. You guys talk in miles, feet. We don't. We talk in meters, centimeters, millimeters, kilometers. Okay, everything is metric. Freezing over here is 0. Boiling over here is 100. Makes sense, doesn't it? Better than 32 and 212. I'm laughing at you. I'm a U.S. citizen as well, so cheers. Don't worry about it. I even voted in your last election. So anyway, but I just happen to live just a little north of Seattle, about 90 miles north of Seattle, so I can speak both languages, okay? 0.002 seconds is 2/1000ths of a second. And in Canada, you'd call that 2 milliseconds. Most scientists in the US would call it that too. Mille, M-I-L-L-E, is French for 1,000. Okay? Cent, C-E-N-T, is French for 100. We've got a lot of French here. You guys got Spanish, we got French. Okay? At any rate, so millisecond, okay? Millisecond is a 1,000th of a second. So 0.002 is called 2 milliseconds. Or if you said 2/1000ths of a second, that's correct too. What's the period of a 1,000 hertz tone? P is equal to 1 over F. F is equal to 1 over P. So period is equal to 1 divided by 1,000. What is that? Well, let's do the calculator. 1 divided by 1,000. Whoops. Do it again, Ted. 1 divided by 1,000. One more 0 is 0.001, 1 millisecond, 1/1000th of a second. Okay? What if you were given the period? What if I gave you the period? I said, what's the frequency of a sound with a period that has 1 millisecond? What's its frequency? You'd go F is equal to 1 over P. Frequency is 1 over the period. 1 divided by 0.001 equals 1,000. Okay, 1 divided by 0.001 equals 1,000. So it's just memorize that. It'll be on your next quiz. I'm going to ask you questions. Here's the frequency. What's the period? Here's the period. What's the frequency? And all you need to know is F is 1 over P. P is 1 over F. Good? Got it? Just great. Well, now I'll talk in my favorite Scottish now. It's just great. All right, now we shall come to the close of today's talk. We've got another 10 minutes left now. Oh, hi. Here we go. All right, we are now reaching the bottom of our page 2. And this is where we finish today, okay? We like to keep these sessions about 60 minutes long. Sometimes we go a little bit over, sometimes a little bit shorter, but I'm hoping that this format is that people are finding this helpful. I can tell I've got better engagement this time around than last semester. We didn't have Zoom last semester. We had a different way. And sometimes no students would show. And it's like you're talking into empty cyberspace, but I would always record it. By gum, I'd always record it. And then some people would listen, but I'll bet you they turned it on and then they went and did the dishes. I don't know. But it's always good to, this is like 100% of your course material comes from these stinking talks on Zoom. Your textbooks are extra. They help look at it from a different perspective, but the nuts and bolts of it is all in these sessions. Okay, wavelength versus frequency. Wavelength versus, we talked period, we talked time it took to take one cycle. Now let's look at the actual length of the wave. How many feet long is it? How many yards long is that sound wave? That's pretty trippy. Now this is, so we're not looking at the time on your watch. What was the length of time to complete one cycle of sound? Now we're looking at how long was one cycle? How big was one condensation and one rarefaction? Here we go. Wavelength is inversely related to frequency. Well, you knew that already. We said low frequencies of long waves, high frequencies of short waves. As frequency increases, look where I'm highlighting here, as frequency increases, wavelength decreases. Recall, period is also inversely related to frequency. Good, you got that, no worries, all good. Wavelength involves the speed of sound. It's the speed of sound. How fast does sound go? What's the speed of sound in air? What's the speed of sound in water? What's the speed of sound in steel? The speed of sound in metric is 340 meters per second. In English or in American, sound goes 1,130 feet per second. 1,130 feet per second. In metric, it's 340 meters per second. What's a meter? A meter is about a yard. What's a yard? 36 inches? What's a meter? 39 inches. So a meter is about like a yard, okay? Close enough. And so sound goes about 340 yards per second, or about 1,130 feet per second. Got that? Good. All right. Now, what is that in miles an hour? Let's take it down to Earth. What's 1,130 feet per second? That's about 766 miles an hour. That's a little faster than a jet with a tailwind. Okay? So sound waves go about a little bit faster than an airplane with a tailwind. Hang on a second. This phone of mine is ringing to beat the band, and I'm just going to pick it up and put it down because it just will not stop ringing. One sec. Honestly. Gadzooks. The phone just kept on ringing. It was driving me crazy. Anyway, so sound goes about 766 miles an hour. What does a jet fly? Around 600 miles an hour. That's what, you know, if you're flying from St. Louis to Kansas City or whatever, you're going about 600 miles an hour. That's what a jet normally flies. Sound goes a little bit faster than a jet. Okay? Once you hit the speed of sound, you break the sound barrier. That's a trip. We'll talk about that next week. But at any rate, wavelength and frequency, the length of a sound wave involves the speed of sound. I'm hearing, I don't know what the heck that is, but at any rate, yeah. So you've got three little formulas here, and they all kind of work together. Wavelength equals speed of sound divided by frequency. That's your most important one. Length of the sound wave is the speed of sound divided by the frequency. But you can figure that out any which way you want. Just write down. In fact, I'm going to write down on here just to bug you. I'll say wavelength over 1 is equal to 340 over the frequency. Over the frequency. So now I'll stop sharing my screen, and I'll just show you here. Every time you see formulas like that, always say wavelength over 1 is equal to the speed of sound over the frequency. That's what you do, okay? It's simple fractions. That's as mathematical as we get in this course. Always do that. If a formula says wavelength is equal to speed of sound over the frequency, always say wavelength over 1 is equal to speed of sound over the frequency. That way you've got 4 numbers to play with, and you can cross multiply. Get it? Okay, so you're going to be doing 1 times 340. So you're going to cross multiply 1 times 340 divided by the frequency. Whatever that is, that will give you the wavelength. Okay? So this guy here times that divided by that gives you that. It's just like 10 over 2 is equal to 5 over 1. blah, 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 blah. Simple, but that's the way the formula. Share the screen again, Ted. Okay, which do I want to share? The desktop. Okay, wavelength. Let's do 100 hertz. Okay, don't worry about wavelength, lambda, whatever the heck that's just Greek, okay? But the speed of sound is constant. In air, it's 340 meters per second. You want to get exact, 343 meters per second. Here it is. Look where I'm highlighting. 343. Big, hairy deal. If you do 340, good enough for me. Okay? Doesn't matter. So let's do 100 hertz. For example, 100 hertz. What's its wavelength? How long is that sound wave? Well, wavelength over 1, look what I did, is equal to 343 divided by 100. Okay? So you're going to do 1 times 343 is 343. You're going to cross multiply. You're doing this times this is going to give you 343. And then you're going to divide that by 100. And what do you got? 3.43 meters. Okay, that's how long it is. Now, I'm talking to people in Missouri, and I'm talking to people in Idaho, and people who don't live north of the 49th. So we'll put it in feet. How fast does sound go? In feet. 130 feet per second. Do the same thing here. Look where I'm highlighting. In feet now. 1, take my 1 here. 1 times 1130 is 1130. And then I'm going to divide 1130 by 100. And what am I going to get? 11.3 feet. Good night, nurse. That's a long wave, isn't it? 100 hertz is 11.3 feet long. That's how long that stupid sound wave is. One condensation is over 5 feet long. One rarefaction is over 5 feet long. That's one friggin' long wave. Okay, but now let's take 250 hertz. Do 250 hertz, and look at here, folks, and I'm giving you an example. 250 hertz, 343 meters per second divided by 250, that's going to give you 1.3 meters. Or you want to do it in feet, 1130 feet per second divided by 250 is 4.5 feet long. So on a piano, middle C, that's the very note, middle C. My father can beat your father at checkers. That's 4.5 feet long. Now gets shorter. 8,000 hertz. 8,000 hertz. And what you're going to do is speed of sound, 1,130 feet divided by 8,000 is going to be 0.14 feet. It's going to be about like an inch. Okay? Real short. So that's just a highlight for you. That the higher the frequency, the shorter the wavelength. So to summarize where we've come so far, and we've covered a lot of ground, good ground today. Okay? Right from the beginning. We talked about sound waves, what are they? And then we talked about longitudinal and transverse. Then we talked about degrees of phase. We talked about 2 ways to represent sound. Waveform and spectrum. We talked about sound taking place in 3 dimensions, frequency, intensity, and time. And we said a sound, a pure tone, we didn't say this, but read this here. Pure tone is a simple sound, 1 tone. Might be 250, might be 100, might be 10, might be 8,000. Those are all pure tones, right? Here, this. A little tuning fork. Teddy will show a little tuning fork. Stop share. Okay. Here's a high frequency sound. Not sure if you can hear that or not, but here's a big tuning fork. Lower frequency sound. Here is a mid frequency sound. Okay? So you got all these little tuning forks. They're different in length. Okay? You got this little guy here. All right? One's going to make a low frequency sound, one's going to make a mid frequency sound, one's going to make a high frequency sound. Those are all pure tones. But most sounds in your environment are complex. They're a mixture of hundreds of frequencies together. My voice, your voices, guitars, clapping, traffic, noise. All these sounds are complex sounds. So they contain many different frequencies together. Okay? But we'll talk about that mañana. That's something for later. Back over to share screen here so that we can finish this puppy here. Okay, then we talked about frequency and period. We did. And then we talked about wavelength and frequency. So frequency and period we covered here. And period, always remember, involves time. Wavelength on the bottom here, physical length of the wave. Both the period and the wavelength are inversely related to frequency. As frequency goes up, the period gets shorter. As frequency goes up, the wavelength gets shorter. Frequency down, wavelength longer. Frequency down, period is longer. Okay? Well, isn't that extra special? So, bottom of the page, important concept for those who fit hearing aids: lows bend, highs bounce. See, now you're learning the lingo of the field. Capital H, small z, low frequencies, okay, hertz. Lows of long waves that bend around objects. Highs of short waves that bounce off of objects. Speed of sound, just for fun, here in the top of page 3. Now you're looking at it. Okay. At room temperature, speed of sound is 343 meters per second, or 1,130 feet, or 1,238 kilometers an hour in Canada. In the States, 766 miles an hour. Look at the speed of light. Look at this. You want to blow your mind? The speed of light is 100 million times as fast as the speed of sound. That's why you see the lightning first, and later on you hear the thunder. The lightning happens right away, and then it takes you a while. Sound goes way slower than light. Light, okay, so we said sound goes 766 miles an hour. How fast does light go? 6 trillion miles an hour. You want to wrap your head around something that'll blow your mind? 186,000 meters, or 186,000 miles per second. 186,000 miles per second. By the way, that's the fastest that anything can go, is the speed of light. How long does it take light from the sun to get to the earth? 8 minutes. How long does it take light to get from the moon to the earth? 3 seconds. How long does it take light to get from your bedroom ceiling to your eyeball? A very, very, very short time. But how close is the nearest star? The nearest star in the sky. Do you know how far away that is? That's 4 light years away. The light from the closest star to the sun took 4 years to get here. So if you were traveling at the speed of light, it would take you 4 years to get there and 4 years to get back. That's why we don't sit there traveling to stars, because we don't know how to go the speed of light. But at any rate, that's light. Just for the heck of it, I just asked you here, if you follow the speed of light, speed of sound is faster in water. How much faster in water? 4 times. It's faster yet in steel. 14 times faster in steel. That's why when you put your ear to a railroad track, you can hear the train coming way quicker than when you're listening for a train to come. Okay? And that's about it. Oh yeah, speed of sound is influenced by the density and the elasticity of the medium. Now these 2 words, circle them, because we're going to come back next week, okay? This is where I end today. Elasticity and density. Density refers to mass. Mass, M-A-S-S. And by that, I don't mean going to church if you're a Catholic, okay? You're not going to mass. Mass is the weight. It's the It's the clout. Think of a locomotive, a train locomotive. That's got a lot of mass. Think of a big rock. That's got a lot of mass. Mass doesn't like wiggling fast. You can't jiggle a locomotive. Okay, you're going to take 100 people to push as hard as you can and 100 people to pull as hard as you can in order to move that locomotive back and forth. It doesn't like moving fast. It doesn't like going changing. Its frequency is going to be low. Other hand, if you have a tight spring, and I'll just cut my share here. I'll stop sharing and talk to you here. If I have a tight spring sticking out of the wall, it's going to be hard for me to push and pull slowly on that tight spring. But if I go, yeah, it's easy. Okay? Stiffness refers to elasticity. Elasticity is the ability to resist being deformed. Okay, it's the opposite of what its word would. You think elastic means wah, 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 wah. In physics, elasticity means how stiff was the object. How much did it resist being bent? Density refers to the mass of an object. Mass can be moved back and forth only very slowly. So guess what sounds go through mass? Low frequencies. When you're in your living room and the neighbors upstairs are playing loud music, what comes through the ceiling? The bass guitar and the drums. Okay? Because it's the mass of the ceiling. That's going to be stiffness. Vibrates or sounds go through stiff objects, yes, but which sounds go through stiff objects? High-pitched. Because high pitches wiggle stiffness. If I have my hand stiff, it's hard to push up and down slowly. But if I jiggle it, no problem. Okay? Do that as an experiment. Take a stiff object and push slowly up and down. You run into a lot of resistance. But jiggle it, no problem. Stiffness lets high-pitched sounds get through. Mass lets low-pitched sounds get through. We'll stop there. It's enough. We've done good. Next week, we're going to finish this section on frequency, wavelength, period, speed of sound, and all that rot. We're good? How are you guys? Doing fine? Cool. If anybody has any questions, feel free to shoot me an email. It's easy peasy Japanesey, okay? My email is Venemat, V-E-N-E-M-A-T, Venemat, V-E-N-E-M-A-T, V-E-N-E-M-A-T at otc.edu. Check it out. All right, if you have questions, I'll be happy to answer them. But I think we have a tighter session this one. I'm really getting a good feel from this acoustics group here. I think we've got better connection. I think we've got more engagement. I think it's, as they would say in Alabama, mo better. All right? Cheers. We'll see you later, okay? All right. Ciao for now. Bye-bye.
Ciao.